Welcome. Very good morning. We are continuing multiple linear regression. In this class, we see the assumptions and estimation of model parameters. Last class, I have introduced the conceptual part of multiple linear regression. Also discussed about the equation form, and the equation we have seen that the parameters beta. So today you will see that how this beta parameters can be estimated.
Okay, now we will see some of the assumptions of multiple regressions. First assumption is linearity. So that is linear relationships. Second assumption is homoscedasticity. Or we say equal y variance across the values of x, otherwise you can say IVs, different observations of IVs, that homoscedasticity. I will show you for how it will be done. Variance across y, across x, y variability remain constant. Then third one is, we have seen that the error term is there, so the error will be uncorrelated error terms. That means there are n cross 1 errors, this vector, this will not be correlated, uncorrelated error terms, and definitely normality of the error terms, normality of the error. So these four assumptions need to be tested. Later on, after fitting the model, we will test this, but at present, at this moment, I should say something about what is this. So first understand what is linearity. You consider your relationships y versus x. For example, it is x1. Then when you plot the data, so if you plot the data, so suppose you are getting this type of relationship. When you are plotting with x2, you may be getting this type of relationship. So in the first case, there is linearity. In the second case, it is a non-linear one. So if your data that y versus x, that relationship is non-linear, then this model is not applicable. What you require to do then? You have to convert this to linearity. You have to transform the data. Primarily we want that you transform IV, first case, from linearity point of view, you transform it, so the data becomes linear, the relationship becomes linear. Now your relationships can be negative, positive, no problem, but linearity is a issue. Second one is your homoscedasticity. I told you just few minutes back that suppose this is my x, this is y, let it be, because as two dimensional, 1 x. Your regression equation, let it be like this. We are assuming that one fitting is possible, linear fitting is possible. So you have collected data points, n data points, suppose this is x1, this one is x2, and then you will go for this one is xi. So similarly last one, let it be xn. So what I said that this observation, this is the first observation, I equal to 1, this is I equal to 2. So like this I equal to n. we are saying that you will collect one sample, but you may collect several samples also. So, under such condition what you will get, and for a particular value of x you may get several values of y. So, if you plot this several y values for a particular value of x, then whatever variability of y you observe, that must be equal. So, that means we are saying this one, if it is sigma square, suppose y equal to 1, so y 1, sigma y 2 square, sigma y 3 square, sigma y n square, I think this is I square. So, what is the condition? Sigma y 1 means at x equal to 1, this y 2 y I y n square, this should be sigma square. This is what is homogeneity from variability of y point of view. If there is violation of this, for example, your plot may not be like this, your plot something this, here it is okay, but here maybe it is like this, here may be against small, here may be against big. So, across x values y is not homogeneous from variability point of view. That assumption if violated, you require to transform variables, but in that case you have to transform the y variable. If there is a linearity problem, you transform the variables, you can go for both, but it is preferable that you transform the x variable. If heterogeneous nature, that heteroscedasticity is there, that means not equal variance is satisfied. So, that in that case you have to transform the y variable. Okay. Then third one is uncorrelated error terms. Actually, you see this equation, this figure. So, when you use regression equation and you predict, you will basically predict these points. For x equal to 1 this value, x equal to 2 this value, 3 I this value, so n this value, getting me. So, the remaining portion is the error. Suppose your case is like this, your original value is here yi, then you are based on this equation, you are saying this is yi cap. So, this portion is my error portion, this is the error. So, similarly everywhere you will be getting error. Error what will happen? Here it is sigma epsilon 1, epsilon 2, epsilon I, epsilon n error. Uncorrelated error terms, because each error is random now. So, the error will follow this type of distribution, epsilon I will follow normal distribution with mean 0, and what will be the variance? Variance will be sigma square, sigma y square. That means, what is this one? Sigma y square, we are writing it is a sigma square equal to sigma y 1 square equal to sigma y 2 square for all observation for equal variance. So, this condition is very important, because we are considering this variability part will be taken care by the error. So, error will follow normality with mean 0 and variance sigma square, where the sigma square is the basically the y variability for each of the observation of x. Now, what we are trying to say further, that suppose there are two observation error terms yi and yk, then the covariance between these two will be 0, that is uncorrelated error terms. So, as there are n errors, so if I see the covariance matrix between the error terms, what will be the n cross n matrix you will be getting? Diagonal elements will be the variance of diagonal elements should be 0. That is what uncorrelated error terms. and normality of the error is this. Error will follow normal distribution with sigma square, variability mean 0. So, these are the assumptions. We will test all those assumptions later on when we feed regression equation and it is required to be tested. Okay. So, once you are satisfied with the data, that examining the data you find out that okay, that assumptions are reasonably valid, then you will go for fitting, that is estimation, modeling or estimation of parameters, estimation of model parameters, that is beta. We are talking about how to estimate the beta, where y is x beta plus epsilon. This is my MLR. This is my MLR. So, if you recall that we say yi is beta 0 plus beta 1 x I 1 beta 2 x I 2. So, like this beta p x I p plus epsilon I, and if we do little modification here, then this will be y I minus sum total of j equal to 0 to p beta j x I j. When j equal to 0, this x I j will take the value of 1. So, if I make a square of it, then you will be getting y I minus j equal to 0 to p beta j x I j square. Okay. So, this is for a particular observation, but we have n observation. So, if I take summation over n, what is this quantity? Sum square error, sum of square errors. So, this one is SSE. Now, we will choose beta j values in such a manner that SSE will be minimum. So, your ultimate optimization issue is here, choose beta in such a manner that SEC is the minimum. Okay. So, you can do very easily this one. So, we can write SSE also in some other way also. What will happen? You have to go for derivation SSE by del beta j, this you put equal to 0. Subject to what? Subject to that your del square SSE by del beta j del beta k, this is it, because it is a minimum case. So, we basically now what happened? We are here also I am saying that only for one variable case beta j, here it is 2 bit variable beta k also we have taken, that means the covariance part is that 2 variables this is coming into. Actually what is happening here, there are so many variables, p variables.
Sir, here should be means del square SSE divided by del beta j beta k or only d2 square.
You are talking about when there is only one variable, we say this by, now if k equal to j, it will take care of that issue. It is general form we have written basically.
Then basically the Hessian matrix.
So, actually that I am trying to say, as there are p plus 1 estimates you are making, so you will be getting a matrix. So Hessian matrix, that matrix will be positive definite. Will be positive definite. That is what I mean to say. That's why I have written like this. Okay. So every component will be calculated and a matrix will be found, and that matrix will be positive definite. By positive definite we mean that suppose A is a square matrix. Now you get any vector in x. If you find out that x transpose x greater than 0, that means A is positive definite. Okay. So what the Hessian matrix will come, that must be positive definite, then it is the minimum condition. Okay. So now let us write in terms of matrix. Then we found out that epsilon is epsilon 1, epsilon 2, epsilon n, that is n cross 1. We are making SSE means square, some square error. Can we not write like this? This is a vector. So 1 cross n, n cross 1, this will give you 1 cross 1 scalar quantity. If this is true, can we not write like this, y minus x beta transpose y minus x beta? We can write, because our y regression equation is this. So epsilon is y minus x beta. You can write like this. Now if I take derivatives against beta, then you will be deriving this one. It is nothing but the square term. So ultimately what will happen? It will come like this, 2x transpose y minus x beta. 1 x transpose will come from here, then derivative, this will remain this, because we are deriving the derivatives for beta, and 1 will come from here, and this with matrix compatibility you will get this equation. So this equation will put to 0. So I can write now that minus x transpose y plus x transpose x beta equal to 0. So I can write x transpose x beta equal to x transpose y. If I multiplied both sides by inverse of x transpose x, then what will happen? What I have done, I x transpose x inverse I multiplied both sides. Now x transpose x inverse x transpose x, in the covariance lecture I have given you that SSCP matrix x transpose x. Can you remember that data covariance time? And I say that this is basically square matrix, symmetric matrix. So the inverse times this will be identity matrix.
As generally it is full rank,
That's why full rank is. So this one is identity matrix. So I can say that beta, we are writing now beta cap, because we have taken the x transposes all these fixed values which are collected from the sample. So this will become x transpose x inverse x transpose y. Okay, so this is your formula for estimating regression coefficients. Getting me? I will show you one example for the estimation part. Let us solve this one problem. Suppose y is 10, 20, 30, 40, 50. This is my 5 cross 1 vector, and my design matrix is 1 1 1 1 1, that will always be there. Then let it be, it is 5 7, then 10, then 12, then 20. We are taking, it is basically 5 cross 2, so that means only one variable, independent variable we have taken. that is x, and this one is your x0. Only one you have taken. Okay. So, what you require to calculate? You require to calculate beta cap, which is x transpose x inverse x transpose y. So, you first find out, your step 1 is find out x transpose x. So, that will be your 1 1 1 1 1 5 7 10 12 20. This is x transpose. Then your again x transpose x only. So, 1 1 1 1 1, then 5 7 10 12 20. Now, this matrix become 2 cross 5, this is 5 cross 2, the resultant will be 2 cross 2 matrix. So, you will get this x transpose x. If you 1 into 1 like this, so there are 5 data points, so you will be getting 5 first. This into this like this. Now, this into this like this, sum of this 5 plus 7, the 12, 22, 34, 54. Other side also this cross this, that also will become 54. Now, 5 into this 25 plus 49 plus 100 plus 144 plus 400. So, 9 plus 5 14 plus 4 18, then 4 plus 4 8 plus 2 10 plus 1 1, 4 4 okay 10, and 4 plus 1 7. So, 7 1 8. Correct. So, you second what you require to compute inverse. So, I say this is my step 1. Now, step 2, I want x inverse x transpose x inverse. So, this is my determinant of x transpose x, that 1 by this adjoint of x transpose x. So, determinant of x transpose x equal to determinant of 5 54 54 718, which is 5 into 718 minus 54 square. This will become 5 into 8, how much it is? 40 plus this 9 35090 minus this quantity will become 16962916, and the resultant quantity will be 674. Okay. Now, adjoint of this matrix 5 54 54 718, this will become, so 718 will come minus 54 5, this will be like this. So, your x transpose x inverse then will become 1 by 674 into 718 minus 54 5. This will become, the quantity will become something like this. If we go by this by this will be 1.07 minus 0.08 minus 0.08, then 0.007. If you go little, but if you want to make it, then 01 something will come for digit case. Okay. Then what you require to know now? You require to know x transpose y. That is another thing you have to compute. Then your step 3 is compute x transpose y. So this one can be written like the x transpose y is 1 1 1 1 1 5 7 10 12 20. This is my 2 cross 5 into 5 cross 1, the 10 20 30 40 and 50. So this is 5 cross 1. So it will be 2 cross, it will be 2 cross 1, resultant will be 2 cross 1. So now the 10 all will be summed here, 10 30 60 on 50 finally. Then this is 50 50 plus 140 plus 300 plus 480 plus 1000. Okay, I think this quantity will become 0. This side, this 5 plus 4 9 plus 8 7, then 4 plus 3 plus 1 8 plus 1 9. This is 1970. Okay, so your step 4 is beta cap equal to x transpose x inverse x transpose y. What is our x transpose x inverse? We found out x transpose x inverse, I think. Yes, x transpose x inverse is 1.07 minus 0.0801 0.0801 0.007 into x transpose y is 150 1970. So this quantity will be, this is 2 cross 2 2 cross 1, it will be 2 cross 1, this into this minus this into this. The quantity will become like this, 160.50 minus 157.80, and it will become 2.70. Similarly, other one will become minus 12.015 minus 13.79. The resultant quantity will be 1.775. Okay. If this is the case, so my regression equation is now y equal to beta 0 plus beta 1 x1 plus epsilon equal to 2.70 plus 1.775 x1 plus epsilon. This is your regression equation, and your y cap will be 2.70 plus 1.775 x1. This is y cap, and if you want to find out the epsilon cap, the error term, that is y minus y cap, which is y minus y cap, you have to find out. So now this one, you have y values, like 10 20 30 40 50, and you require to find out y cap. How do you find out? You have x values also. X values are 1 1 1 1 1, then 5 7 10 12 20. Okay, so it is 2.70 plus 1.775. What is x1 value? 5. 2.70 plus 1.775 x2 value 7. 2.70 plus 1.775 x3 value 10. 2.70 plus 1.775 12. 2.70 plus 1.775 into 20. This will give you your error values. It will be 5 cross 1. Okay. I think this is what is estimation. We have calculated very simple problem, only one variable at a time. So when you take y is function of f(x) in the linear mode like beta 0 plus beta 1 x1, plus epsilon, only one variable. This regression is known as simple regression, simple linear regression, when that means p equal to 1 case, p equal to, now if it is p is number of parameter to be estimated, then it is 2 intercept plus this. And if I say p is the number of variable case, this is only 1. So, when it is p greater than equal to 3 or more number of parameters to be estimated, or other way I can write p plus 1 if should be 2, then it is simple regression. When p plus 1 greater than equal to 3, that will be multiple regression. Okay. But all those cases y is a single dv, y is our single dv. Okay. Only one dv at a time we are considering. So, next class we will see the sampling distribution of beta. Now, beta you have estimated, this beta cap, I am saying sampling distribution of beta cap, that estimate basically. So, this beta cap you have estimated using a sample. If you go for several sample, the beta cap value will change and it will become it is a random variable. What about beta? Is it a random variable, the beta, the regression coefficient from population point of view? You have y equal to x beta plus epsilon, which we are talking about. It is our regression line for the population. Beta is the population parameter. So, that constant and it is unknown. So, that is why you are obtaining this beta cap, which is estimate of beta, and expected value of beta cap will be beta. This is the unbiased estimation. Fine. So, beta is constant and random, constant and unknown, and beta cap is random variable, but it is known now. When you are collecting data, you are getting this value. So, we will go for sampling distribution of beta cap. Okay. Next class.